focus on three types of relationships. First type of relationship is congruency. Okay. Then the next one will be incongruency, and then the following one will be similarity. Okay, which talks about like scale factors and dilations and that kind of stuff. So those are kind of the overarching concepts that we investigate as we move through the course. Now, there'll be other things that we do, but those are the main kind of topics. So talking today, we're going to start talking about congruent figures. And today, we're collectively talking about all types of figures. Okay? Tomorrow, I guess Monday, we will kind of retrace ourselves, go back a little bit, and talk simply about triangles. Because the idea is if we can learn a lot about triangles then build together to create rectangles, pentagons, hexagons, all types of other shapes. Okay? So triangles are kind of like our building blocks for everything else. So if we learn a lot about triangles, ultimately we learn a lot about everything else. Okay? So talk about congruent figures and kind of the foundation that needs to be laid for us to deal with ultimately congruent triangles next week. Congruent figures are, we talked about congruency before. It's the same thing. We did it with segments and we did it with angles. Now it's a little bit more involved because we've got more angles and more segments in each shape. But it's basically saying the same exact thing. If you have two figures that are the same size and they are the same shape, they will be considered congruent. It's the idea that if we're able to cut and paste one shape and lay it on top of the other one, then you have congruent figures. As we start talking about congruent figures, we're going to start naming them, and we name them off their vertices, okay, off the points that define their endpoints of the segments. And the order that we name them, the order that we basically list those points is going to be important, okay? And it's not necessarily like a mathematical competency. It doesn't mean I'm going to have to add, subtract, multiply, divide. I'm doing that kind of stuff. But it becomes a very big concept that if you fail to abide by it, it will really mess up everything else and all your other understanding beyond this point for this class. So it's something we must make sure that we understand the procedure before we go on. It's kind of like, if I'm in English class and I'm writing in APA style. You guys talk about APA? Like how you format your paper, that kind of stuff? MLA, you do that? Okay. So if I'm using those formatting tools and I don't format my papers correctly, am I going to be docked for that in the long run? Yes. Okay. So this is kind of how we format our work inside geometry. If we don't abide by the rules of this formatting, we're going to miss out on things. Okay. We're going to have some issues. So that's what that second bullet is getting towards or getting to, is that we have to be able to name things correctly. All right. Basically, when we start talking about congruent figures, the idea is that all of our segments that are going to be congruent need to correspond. They need to match. And all the things that match need to be congruent. Okay, so it's kind of a two-way street. All the angles that are going to match or correspond need to be congruent, and all the angles that are congruent need to correspond or match to one another as well. So here's the idea. I've got these pictures here. What I want to do is just kind of make the argument that segment AB, would you guys agree that segment AB is going to match? AB is going to match to XY? That makes sense? Okay. So if they're congruent, I'm just going to say AB is congruent to XY. Use a different color so you see them better. AB is congruent to XY. Okay. BC, what's BC going to be congruent to? Why is it? And then AC is congruent to XZ. And we're just making this argument based off the markings that are in the picture. Okay. So this is the size that corresponds. Here's the idea of what we're really doing. I were to take that shape right there, trace the best I can, does that shape, when I transfer it, does A, B go on top of X, Y? A to B, does that match up to X to Y? Does that make sense, everybody? Same thing about BC. Does BC match to YZ? And does AC match to XZ? And that's hopefully the case that's happening there. So if I look at the angles that match, what's angle A going to match to? Again, if I overlap these, A goes to X, right? What's C go to? Z, and B is going to then go to Y, right? So A goes X, B goes to Y, and C goes to Z. Okay? That is information that we know that's going to be true when these two triangles are congruent. If that's the case, then I want to be able to write what we call a congruency statement for these two triangles. Okay, so I'm going to come down here and write congruency statement. Okay, and basically all you do when you write a congruency statement about whether it be triangles, rectangles, pentagons, octagons, whatever they may be, any polygons, you first identify what you want to name your first figure. Okay, so with triangles, we'll talk about when we get to other polygons the importance of a certain process in naming them. But for triangles, you can just take the three letters and put them in any order that you want to. Okay? So in triangle, that gray one on the left, maybe just to kind of break the normal routine, I'm going to go like CBA. CBA. Most people would say like ABC, right? They put it alphabetical. Okay? Let's go to CBA, because you can name it any way that you want. Okay? Now, if I name the first one CBA, when I name the second one, I have to follow the same pattern that I used when I named the first one. Meaning that when I said C in the first triangle, I had to figure out in the blue triangle which angle matched to C. So which one was it in the blue that matched to C? Z. I need to write Z first. And then we went to B in the first one. So it's C to B. So then I can go Z to what? Z to Y. And then obviously the last letter that's available to us would be X. Okay? And here's the argument, guys. We need to be able to write it that way. CBA congruent to ZYX. Because just by looking at the name, completely ignoring the pictures, the pictures weren't even there, I should be able, you should be able, to take these first two letters, CB, and these first two letters, ZY, and make the argument that they're congruent. Does that make sense? So the order in which we write our names tell us which segments are congruent to which segments without using the picture. So CB is congruent to ZY. Now, can I say CB is the same thing as BC, and ZY is the same thing as YZ? And when we talk about congruent segments, we can name them. We can reverse the names of segments. We start at B and go to C, or C and then go to B. Okay, can I look at the last two letters? BA and YX. BA and YX. Or BA and YX congruent? That make sense? And then the last set of segments that we got to look at are the first letter and the last letter. So C and A. And then over here would be Z and X. C and A, well, that's AC. ZX, the same thing as XZ. So they are congruent. So just by knowing that name right there, I can identify which segments I know have to be congruent. And I should be able to do the same thing with the angles then. If I look at angle C being the first letter, then angle Z is the first letter in the other name, right? So C and Z must match up. B and Y, and then A and X. Does that make sense, everybody? Now, that's the way I named it initially, but some of you might have said, I'm just going to name it ABC,
Well, if you name it ABC, then you have to be able to name the blue one the same way. So if you go A to B to C, then you need to go X to Y to Z, because now AB should still be congruent to XY, and we see that it is right there. We should be able to say BC is the same thing as YZ, and it is. We should be able to say A to C and X to Z are the same. Does that make sense? My argument of talking about this, and the reason we talk about this as much as we will throughout the next couple of days, is if you don't pay attention to that formatting, much like if you don't pay attention to MLA style formatting, you're going to miss out. You're going to miss out on points. Now, the idea in math is that if I don't pay attention to that, I'm going to think that when Mr. Fay talks about triangles the way that he named them, and I didn't name them the same way, I'm going to think I'm completely wrong if I don't understand this concept. And I'm going to go throughout the entire year thinking every single one of my problems is wrong, or some aspect of every one of my problems is wrong, where you're actually doing everything correctly. Does that make sense? And that could be very detrimental to your development and ultimately your grade. Okay, so that's something to pay attention to and think about. You can't just be willy-nilly about naming these. There has to be a procedure. Okay. This kind of goes on and extends that idea beyond triangles and starts talking about just congruent figures in general. Okay, congruent polygons. A congruent polygon just means they have corresponding parts that are congruent. Okay, it basically means they have the same size and the same shape. So if I look at those, the last two triangles that we talked about, they were kind of like a translation of one another. They were a cut and paste directly of one to the other, where if I do that here, I'll trace this out. If I cut and paste this one, is it a direct match? Cut and paste this? It's not a direct match, right? Okay? So the idea here, this is where people often struggle. I think it's kind of obvious in these pictures, but angle A, just because it's the top left angle, does not mean it's congruent to angle F because it's the top left angle. Does that make sense? Okay. We need to be able to match up that vertex there A to this vertex here at E. Basically what's going on here with this particular set of figures is that it's a reflection across that line right there. So A would land on E, B on F, D on H, and C on G. The idea is just from these names, you should be able to tell me that AB, what segment is AB going to be congruent to? Just by looking at the name. Don't even look at the picture. EF, right? First two here, first two there. Okay. What should BC be congruent to? FG, good. Okay, so that'd be the second two. The third grouping would be C and D. What should CD be congruent to? GH. And the last one that we struggle with a lot of times, if I go ahead and put these markings in, so we're A, B, and EF, BC, and FG, and then we did these last ones here, CD, and GH. So the last set would be AD and EH, right? If I look at AD and EH, those are the first and last letters of the names in both those figures. And that's the one that people struggle with finding the most, is that last one. I choose the first letter and the last letter. So that's just what that's the quadrilateral. Two quadrilaterals congruent. So we got 4 sets of segments congruent. If I had a pentagon, I'd have 5 sets of congruent segments. If I had 2 octagons, I had 8 sets of congruent segments. Okay? So just kind of be on the lookout for that. Now, angle A would be congruent to angle what? Angle E. Angle B would be congruent to angle F. Now, look at this is, I think, important to talk about. If I look at angle B and compare it to angle F, angle B, it's made by segments in which one segment has one
hash mark in it, and the other segment has 2, right? If I look at angle F, is it created by segments that have 1 hash mark and segments that have 2 hash marks? Does that make sense? Being able to visualize that and seeing that similarity, that relationship that this angle, angle B, is made by the same type of segments. Angle B is made by the same type of segments that angle F is made by, is going to be very important for us in the coming weeks. Okay? And then angle C is made by segments that have 2 and 3. And then if I go to the figure on the right, well, which angle is made by segments that have 2 marks and 3 marks in it? It'd be angle G, right? So C and G should match up to correspond. And that is then verified within the names as well. Is that all right? Does that make sense to everybody? What they're going to do, so practice problems that we're going to see is that they're going to give us something of this form. Let's just erase this real quick. They will give us, we go like that, and they will hide that. We'll hide the congruency statement. They'll give you the pictures and ask you to write the congruency statement. Does that make sense to everybody? Okay, so hopefully with the information that's there, we can do that. Okay? The next thing they will do, or the other thing that they will do, is that they will hide the picture, give you the congruency statement, and ask you to come up with this information here. Come up with the 4 sets of segments that are congruent. Come up with the 4 sets of angles that are congruent. Okay? If we can play that game forwards and backwards, we should have success within the next couple areas of this course. Okay? So I'll kind of do that with you here. If I have, erase these are the answers. If I have these 2 figures, H, I, J, K, it's congruent to L, M, N, O. Okay? So because I have 4 vertices, that means I have a quadrilateral. 4 letters, 4 vertices, 4 sides, quadrilateral. Okay? So quadrilateral congruent to quadrilateral. If I say I want to look at the side, okay, what is going to be congruent to HI? LM, right? Okay? So HI is congruent to LM. What's going to be congruent to, I can't move that. What's going to be congruent to IJ? MN. IJ congruent to MN. What's congruent to JK? NO. And then the last one will be H to K. What's HK going to be congruent to? LO. L. The other one's fine. So here's the thing, like, I write it as HI congruent to LM. Somebody else might write it HI congruent to ML. That's fine. That says the same thing. Somebody might say IH congruent to LM. That's fine. It says the same thing. Somebody might say IH congruent to ML. That's fine. It says the same thing. Does that make sense? There's a lot of different ways you can say that first congruency. Just because we know we can reverse IH and HI, we can reverse LM, and then we can reverse that congruency statement. We can read it from the right to the left. So it gives you a lot of different options on how you can specify which segments are congruent to one another, which is nice, but at the same time, if we're all trying to be on the same page, it can kind of be a pain in the butt. Okay? Because there's so many different ways that we can say, yes, this works, this is true. If we go angle, obviously it's kind of easy with angles. So if I go angle H, what's angle H going to be congruent to? Angle L. What's angle I going to be congruent to? M. So then J goes to N, and K goes to O. So that's kind of easy naming them with one letter, right? Okay. What if I did this? This might be something we have to do eventually. What if I said angle KHI? What should angle KHI be congruent to? Think about how you went and wrote this. You started at K, and you jumped to the beginning at H, and then went to I, right? So come over here and follow the same pattern. Start at O, jump to L, finish at M. So angle OLM. If we look at our pictures then, KHI should be that angle right there. And OLM should be that angle right there. Okay? And my argument, guys, is when we look at just that picture without any markings in it, I don't know how many of us would be able to accurately say, I don't think I'd be able to do this, that H and L are the ones that match up. Because I think some people might say, well, I and L actually match up because they look like they're the same. Or H and M match up or something like that. Does that make sense? Because they both look like kind of the same acute angle, don't they? Okay? But if I use the congruency statement that's provided, I'll never make a mistake with this stuff. You don't need to write this down, but when we're talking about making shapes congruent, there's two things that have to take place. You have to have the same shape, and you have to have the same size, right? The sameness in regards to shape occurs because they're both going to have the same amount of angles. And those angles are going to correspond. Okay, they're going to match up. The same size aspect is verified or created because the corresponding sides are congruent. Okay? So size is dictated by the side length, and shape is dictated by the angles and the amount of angles that we have. Okay? So that's something to kind of ponder and think about a little bit. Okay? These are, to get some examples here, this is the kind of question they're going to ask you. If you have this picture, and we want to talk about whether those two figures are congruent, we have to be able, since we have triangles here, we have to be able to find three sides congruent to three sides, and then three angles congruent to three angles. Okay? Explicitly, they only tell me maybe two angles congruent to two angles. Angle A is going to be congruent to what? Angle E, right? That's explicitly given. When I mean explicitly, they come straight forward and tell me angle A congruent to angle E in the picture. What is angle B congruent to? Angle D. Okay? With that information, there's several different ways of coming up with a third congruency for angles. Okay? Would you guys agree that this angle here is the same as that angle there? Why? Vertical angles. I think that's the most obvious one there. Vertical angles. Would anybody agree that we also have, think about this. If this is angle A, let's just say was 20 degrees, doesn't angle E have to be 20? If angle B, let's say, was 80 degrees, let's make it 100 degrees. What angle D has to be 100 degrees? And what does this angle here have to be? 60. And what's this one have to be? 60. And that would be true no matter what numbers I chose other than 120, right? You guys remember the third angles theorem? If two angles of one triangle are congruent to two angles of another triangle, then the third angles have to be the same because they're both triangles have how many degrees that you're allowed to use? 180. Okay? So third angle theorem. Would you guys agree that this angle here is supplementary to that angle there? Does that make sense? Well, my highlighter stopped working. There we go. Would you guys agree that this angle here is also supplementary to the orange one? Because remember we're talking about the fact that you have two angles that are supplemented to the same angle. So we have these two orange angles that are both supplementary to the blue angle. Then the orange angles have to be the same. That was the congruent supplement theorem that we talked about probably about 3 weeks ago. So there's a lot of different reasons. Now, the most obvious reason, I think, what Landon shared with us, is that they're vertical. Okay? So, come on. Sorry. So I think the fact of saying that they're vertical is obviously the most apparent reason. Now, can I just say angle C? Can I say angle C? Can you angle C here? If I say angle C, are there different places you could look? Could angle C be this angle here? Or could it also be that angle? Or that angle? Or that one? Does it make sense? So when you have multiple angles sharing a vertex, you can't just call it angle C. So I have to say angle like BCA. Okay, because now there's no ambiguity in what angle I'm talking about, right? I know for certain if I trace from B to C to A, what angle is being traced out. Well, if I go from B, C to A, and I know what I'm talking about this angle over here being congruent to it, where do you think I should start over here in naming this angle here? I go start at D. Okay, so notice here on this one, I started at B because it had 2 marks in it. I went to C and went to A. So if I start with 2 marks here, I should probably come over here and start with 2 marks. If you follow that plan, things down the road are going to be very simple for you. Okay. Now, if you wanted to call it ECD, is ECD the same angle as DCE? If I put my finger on E and go to C and then finish at D, is that the same angle as if I started at D, went to C, and finished at E? They're identical, right? So if you want to flip that name, that's fine. But down the road, that will get you into trouble a little bit. All right, so I think this is the best way of approaching that. Is AB, what segment is AB congruent to? ED. Okay. What segment is BC congruent to? It's a unit or a distance of 4 units, right? Is there another segment up there that's a distance of 4 units? Yeah. Are they both segments? Are they the same size? That meets the definition of congruent segments, right? So they don't have to put the markings in, and they gave me the values. Well, that's fine. So DC and BC are congruent. And the last one would be AC congruent to EC, right? They're both 6. We show 6 congruencies there. So those shapes are congruent. Okay? Now, we need to name them. I'm going to write a congruency statement. So my congruency statement here should be, what do you want to name? You have options. You can either start in the triangle on the left and name it anything you want. Or start in the triangle on the right and name it anything you want. It does not matter. Okay? So if I start with let's just start with the one on the left. What do you want to call the one on the left? Using those 3 letters. Anybody? Okay, I heard A, B, C first. A, B, C. Use. Okay. So you had some choice there. But when you make the decision to call that A, B, C, that's going to dictate then the way that you name the second one. Because when I name the second one, those 6 congruencies that we wrote above should be maintained. So when I have AB up here, right here, AB congruent to ED, these first 2 letters better be ED or DE. Does that make sense? Okay. So my philosophy is if I went A, B, C, I went from A that had 1 mark in it, I went to B that has an angle that has 2 marks in it, right? So over here, where should I start? E that has 1 mark in it, and then go to D. So it tells me the right order to put those 2. Instead of DE, it needs to be ED. And what would be the third letter that I have to follow to? I have to go to C. And now inside that set of names should be the 6 congruencies that we have listed above. Is it okay? Does that make sense? We need to be able to go from those 6 congruencies down to those purple names, and we also need to go from those purple names up to the 6 individual congruencies. Okay? But this statement here, that's called a congruency statement. You're going to see that in your homework. You see it in tests and quizzes. I'll give you either a picture like this. I might give you just the angles and segments that are congruent, and I'll ask you, write a congruency statement. I'm looking for you to say what shape is congruent to what shape and have the right order of those parts. Okay? Now, that being said, could I have said BCA? If I started at B, went to C, finished at A, where should I start over here? D, and go to what? C, and finish then at E. And that shouldn't say, well, BC and DC should be the same. BC, DC, yep, they're the same. AC and CE, AC and CE, they should be the same, yep. I should be able to do that with all 6 parts up there if I name them correctly. Is that all right? So the issue is that in a class, when I say ABC is equal to EDC, but on your homework or in your notes you wrote something different, your different thing might still be okay. All right? So you have to be able to analyze that on the fly and make the argument to yourself, yes, I'm doing everything right, and I'm staying on pace with everybody else. All right. I don't know what happens here sometimes when I transfer from PowerPoint to OneNote. It changes specifically the triangles into whatever that thing is. That should be a triangle there. And so should that. Now, you don't need to write all this down. You don't even need to maybe write this slide down at all. But what's the relationship that we're saying here between the 2 triangles? They're congruent. Okay? Now, F should match to what? D. Okay? So F is an angle, D is an angle, right? Well, those, more generically, are just parts of a triangle. Do you guys agree with that? Okay? But F and D match. F and D match. Another word for match in math is corresponds. Does that make sense? Okay? So, F and D are corresponding angles, right? Does that make sense? But more generically, they're corresponding parts. They're coming from what kind of triangles? What was the relationship you said between the triangles? Congruent, right? So you got corresponding parts coming from congruent triangles. What's the conclusion that I know about F in angle D? Angle F and angle D, they have to be what's one another? Congruent. Okay? So we put all that stuff together, we get this phrase here that says corresponding parts, matching parts, or draw the pictures, the overlapping parts of congruent triangles, meaning they came from triangles that we already knew to be congruent. Well, this statement says that if that's happening, then those 2 parts that you're talking about are actually congruent to one another. Okay? So the idea then says if I give you triangle AWS is congruent to triangle MNO, you should be, if I know those triangles are congruent, you should be able to tell me which parts are congruent then, right? What's AW congruent to? MN. What's WS congruent to? NO, right? Does that make sense? And we can do that with all 6 of the parts that are up there, segments and angles. All right? The short of that is this acronym that we call CPCTC. Okay? At first, it's kind of hard to say, but eventually you'll get to it. CPCTC. Corresponding parts of congruent triangles are congruent. When you write this, maybe your first couple times, you might want to put those symbols above those C's because it stands for the word congruent. Okay? A lot of times in the past, I get people say, congruent parts of congruent triangles are congruent. That's a pretty redundant phrase, okay? And you really don't say anything that people didn't already know. Does that make sense? If I have congruent parts of congruent triangles, they're congruent. Yeah, that makes sense. Or corresponding parts of corresponding triangles are corresponding. Or corresponding parts of congruent triangles are corresponding. That doesn't say anything new, right? It's when it's corresponding parts of congruent triangles are congruent. That says something new to us. Okay? So we got to make sure that we know what DC stands for. and what that one stands for. We'll use that a lot. Probably makes sense to write down that bullet, but not the bottom one. It's an if and only a statement. Biconditional. Okay? So what this is saying, if I want to show two triangles congruent, I have to show all corresponding parts to be congruent. So in a triangle, I need three angles congruent to three angles, and three sides congruent to three sides. I got to show 6 total things. Okay? If I've got quadrilaterals, I got to show 4 angles congruent to 4 angles. 4 sides congruent to 4 sides. That's 8 total things. Okay? And you can start to maybe extrapolate that and say, okay, well, if I've got dodecagon, you know how many sides a dodecagon has? Do you remember? Dodecagon? Decagon's got 10. Dodecagon is, somebody say 12? Dodecagon's 12. So then I need to show 12 sides, congruent to 12 sides, 12 angles, congruent to 12 angles. That's 24 things, right? That's going to be a pain in the butt. You're going to find out that showing 6 things is a pain in the butt. Okay? A lot of things that we do, there's not going to be enough information for us to conclude that there are 3 angles congruent to 3 angles and 3 sides congruent to 3 sides in 2 separate triangles. So you do that with 12 angles and 12 sides, you can figure out that that's going to be almost impossible. Okay? But this idea says if you're able to do this, if you're able to show all corresponding parts to be congruent, then the figures are congruent. It's an if and only if statement, so you can reverse and say if your figures are congruent, then you can pull out the corresponding parts and say the corresponding parts are congruent as well. Okay? The rest of chapter 4 is actually an investigation of how we can do this with triangles much easier than saying 6 things congruent to 6 things. We'll break it in half and we'll say maybe 3 sides congruent to 3 sides. We'll guarantee triangles to be congruent. I don't have to look at the angles at all. Okay? So that's kind of what we'll do on Monday. Let's do one problem here, one example. We've got this, and this is what they're going to do in your homework. They're going to give you 2 shapes. They're going to give you a congruency statement, but these shapes are a cut and paste of one another. They've been either rotated or flipped, that kind of thing, to where you can't just say, oh, I'm going to take the right segment and set it equal to the right segment, or the left segment, set it equal to the left segment, or something like that. Okay? Number one wrong answer, trying to find y, is that people say, well, 7y plus 9, that's bottom left. 87 is bottom left, right? They say, well, they're congruent. They're not. Why are they not? Well, what should they be equal to? You say it, Skyler? Yeah, if this is true here, if I've got that congruency, angle E, and why do I choose angle E? Is because I'm looking for y. That's my goal, is to solve for y. So I'm going to look at the object, okay, whether the angle or the segment that has y attached to it, and that's angle E in this case. So in the name, angle E corresponds to angle N, right? So if the shapes are congruent, then those corresponding parts are congruent, right? So 7y plus 9, which is angle E, should match up to angle N, which is 72. And once we have it, I'll let you solve it, but 7y plus 9 is equal to 72. Okay, the next thing I want to do is solve for x. So I go find the object that x is attached to. It's attached to segment GH here, right? Attached to that segment there. So GH is the last 2 letters here. So what should it be congruent to over here? LM. So I go find LM, and it's that segment there. Okay, so we'll write 2x minus 3 equals 8. And both those equations are the things that I think we should be able to solve on our own. But the idea, what happens here, and they'll fill in a lot more stuff into these pictures. So they'll give you what MN is, they'll give you what LP is, they'll give you EF, FG, EH, all kinds. They'll give you a lot of stuff. Okay? And you got to make sure that you're able to pair up the right things. Okay? Does that make sense? Obviously, if they would just give me, can I wipe that away, wipe that away, wipe that away, wipe that away, wipe that away? They just gave me that. It's kind of easy without even having any math background. If I knew I had to solve what, what's set equally, right? Okay. So we'll add things in there that are going to be detractors, and I have to then rely on that statement there to be able to do that problem. So like I said, Monday, we'll go backwards a little bit. So this was talking about all types of polygons. So I can do this with 5 sides, 6 sides, 8 sides, 100 sides. Monday, we'll start focusing just working on triangles. Okay. There is an assignment in Math Excel. Shouldn't take you very long.